So extra example number 3 is from section 12.2, transforming to achieve linearity. So we're looking at under age 5 mortality rate versus income per person. There's this website, gapminder.org. It's a nonprofit website that has a bunch of data. And so here's a scatter plot of the original data, and you can see it's not linear. And in fact, it looks like the graph of y equals 1 over x, right? Where the x and y axis are asymptotes. So it looks like y equals 1 over x, which is the reciprocal function. So if you, instead of using this original data, if you plot the reciprocal of x, so instead of using under 5 mortality rate, you use 1 over that number, it actually makes it more linear. And so and likewise, if you take the reciprocal of income, it also makes it look more linear. So those are two different possible transformations. The data, if you do transformation 1, is here. And we can see the y-intercept, slope, r squared, and the standard deviation of the residuals for the first transformation, and the residual plot. And then we can see if we do the other transformation, here's the data and here's the residual plot. So we are going to do the so we are going to give the equation for each least squared regression line. So we want to equation of the least squared regression line for each transformation, predict the income using each of the different models, and then interpret r squared for this one. Okay, so this is extra example number 3. So part A. So if we look at transformation 1, if we wrote the equation for the least squared regression line, we would get that the income, the predicted income, so we use a hat over it for predicted, equals the y-intercept, which is 869 plus 104,868. And since we did the reciprocal of mortality rate for under 5, we would do over under 5. And if we use the second transformation, transformation 2, we get 1 over the income, predicted value equals negative 0.0000585 plus 0.0000829 times x, which was under 5. So that's part A. And then if we use each of those models to find the income per person for Turkey, if we use the first transformation, we would get income equals 869 plus 10,4,868 over 20.3, which should give you 6,034.91 if you use your calculator. And if we use transformation 2, 1 over the income is negative 0.0000585. So this is what you'll be doing. You'll be writing the regression line model and then using that to find the predicted value. That's 20.3. 20.3. That's our mortality rate that we're given. Just plugging in 20.3 into each equation is what I'm doing. So solving for that, 1 over income equals 0.000162437, and then just take the reciprocal to find the income. So So the income equals 6,156.23. And then interpreting r squared in transformation 1, it means the r squared is 84.3%, 84.3, so that means 84.3% of the variation in income in the y value is accounted for by the least squared regression line. Is accounted for by least squared regression line, where we use x is 1 over the mortality rate. And for transformation 2, we would say 92.1% of the variation in the reciprocal of the income, 1 over income, is accounted for by the least squared regression line using x is the under 5 mortality rate. And if we had r squared equals 100%, then every point would be on the line. So the predicted and the actual values would be the same. Okay, and then extra example 4 is more M&Ms. Example 4. More M&Ms. So we are looking at a student opened a bag of M&Ms and ate all the ones with the M on the top, and then put the remaining 30 back in the bag and repeated that over and over again. We don't know how many were in the original before, and those are course numbers as far as for feeding on the M&Ms. Course number 1, 2, 3, etc. So if we just look at if we just do a scatter plot of the original data, it does not look linear. But if we take the natural log of the number of M&Ms, so you can see it says natural log remaining, then it becomes more linear. So what that means is that explain why it'd be reasonable to use an exponential model. So like we talked about in the notes, if we take the natural log of y and it makes it linear, then an exponential model is reasonable to use. So you would say, so this is number 4 on M&Ms. For A, you would say, then, since the scatter plot of x versus the natural log of y is roughly linear, it is reasonable that the original data, follows an exponential model. So that's for A. Okay, and then for B, so we have the Minitab output here, and we're asked to give the equation of the least squared regression line defining any variables we use. So for part B, we would say that the natural log of y equals 4.0593, the y-intercept, minus the slope, 0.68073x. The natural log of y, this is the predicted value predicted value of the natural log of the number of remaining M&Ms. The number of remaining M&Ms, and X is the course number, meaning first feeding, second feeding, etc. X is the course number. So that's the equation of the regression line, and then use our model to make a prediction. So if we want to know the original number in the bag, that would be course number 0, so we just plug in 0 into this equation, minus 0.68073 times 0, that goes away. Okay, we get to do a little bit of math to solve this. So we have the natural log of y equals 4.0593. So natural log of y means base e, so we're saying e to this power equals y, if we just rewrite it. So y hat equals e raised to the 4.0593 power. So on your calculator, that gives you 57.93 M&Ms for the original amount. And the last thing I think we're asked is to look at the residual plot. So we want, in our residual plot, we want to have a just random kind of scatter about the residual equals 0 line. And we do. There's no obvious curvature there, so the model seems appropriate for the data. So for part D, we would say something like, since no obvious curvature in the residual plot, model is appropriate for the data. Model is appropriate for the data.